Hi everyone, my name is Nacha. I'm the first author of this paper. I'm from the University of Auckland in New Zealand. It's my pleasure to present my paper today. This paper focuses on supporting the architectural migration using formal techniques such as ontology reasoning and model checking techniques. So let's get started. So today I'm gonna start by discussing the motivation of this paper regarding the architectural migration, and then I will present the highlight of the contribution of this work. As this work is based on the formal techniques, we will firstly look into how we formally define the software architecture design. After that, we will look into how can we refactor the design to support a new architectural style. Then we look into how can we make sure that the refactor style is correct through the formal verification. Then I will briefly present how-to and evaluation result, and then I will conclude this paper. As a software architect, when we design software system, we look into new technology or principle that can be applied into your design because you want your software system to be state of the art. For example, like microservices, cloud, containerization that would provide you flexibility in development and deployment, or blockchain technology that would provide you the way that you can build the decentralized database system that would be protect from data tampering. If you design the system from scratch, that would be easy because you start from the blank page. You have no existing design that you need to be concerned of. But most of the time, you're not that lucky. You have existing system that is designed decades ago. So you would need to look into the existing design or the pattern that has been applied to it and try to transform the design without changing the system functionalities. This is what the architectural migration is about. So based on our literature review, there are existing works that focus on this kind of migration to support the software modernizations. Most of this work focusing on the implementation level by refactoring the source code from one style to another, or supporting some particular architecture style like transforming monolithic architecture into microservice architecture. But the big challenge is how can we ensure that the refactor design would preserve the existing system functionalities. To our knowledge, there's still lack of approach that address this challenge and generally support the migration by both refactoring and verifying the design at the software architecture level. So we develop an approach to support this migration. The overall process starts with the current design that needs to be refactored. We apply ontology reasoning that help to identify the entities that need to be refactored and perform refactoring. As a result, we get the target design, which are later verified by the model checking technique to ensure that the functionalities are still preserved and the design comply with the architecture pattern that apply into the design. To support the migration, we formally define a model to describe both structure and behavior of the software architecture design. We develop our modeling based on EMF, Eclipse modeling framework, which will help us to describe the design in component and connector view and deployment view, which represent logical and physical architecture design. The model can be converted into OWL, which will help to describe the structural aspect, such as how components are connected to each other. And also, it can be converted into ADL to describe the behavioral aspects, such as how components are interacted to each other. We also define the architectural patterns, such as publish, subscribe, or client server, and also some of the modern software system pattern like event sourcing or CQRS, which is widely used in the event-based microservice architecture, or Oracle and reverse Oracle, which are used in the blockchain architecture. To refactor the design, we define a rule that consists of two parts. The first part is ontology definition, which describes what design element to be refactored. And second part is a step to refactor the design. For example, this is a rule for event sourcing pattern. What it does is converting the publish subscribe into the event sourcing. So you can see that the ontology definition would look for PS connector, which is publish subscribe connector that process the event in the system. And then the first step to refactor is to change the type of connector by mapping the role from publisher to event publisher or subscriber to event subscriber. And then we add a component which is event store that help log every event that coming in according to event sourcing pattern. And then we connect them together. And this is another example of rule. This rule converting the repository pattern into reverse oracle pattern that read the data from the blockchain. So you can see that it convert the repository component into the reverse oracle component. Instead of storing the data into itself, it will store the data or read the data from the blockchain, and then add a connector, attach a port, and connect the connector together to the blockchain component. So in summary, the step to refactor is mostly it would map the role of the connector, add the component, or connect the design element together. In our paper, we use LiveNet as an example to demonstrate our approach. So these diagrams show some part of the design that has been refactored. The gray highlight what has been changed. For example, the request log component has been added. Notifier has been changed from publish subscribe connector into the event sourcing connector. The med chain has been added as a blockchain to store some of the data, and the connector has been changed accordingly to interact with the blockchain. So after refactoring, we will verify two things in the target design. The first thing we verify is functional requirements, which we formally describe it as a linear temporal logic. This logic describes how components interact with each other to serve the functionalities. For example, in this case is handled when the emergency is requested, what need to be done or what component should behave. The other thing that we verify is verify whether the target design behave according to the pattern that are applied. For example, we make sure that every event is logged in the event store according to the event sourcing pattern. We have implemented our approach in a supporting tool called Arc Modeler. So this Arc Modeler which allows the user to visually define the architecture design in graphical diagram and also identify the design to be refactored, generate the architectural constraint according to the pattern, and also make the verification. So all can be done on this graphical user interface. We have conducted evaluation on 4 different software systems. So based on our result, the refactoring rules has been proved to be soundness, as the system design has been refactored, all key functionalities are still preserved. And all design entities that require changes are refactored, so our refactoring rules are proved to be complete too. In conclusion, we present a formal approach that helps to support the architectural migration. Our approach can automate the refactoring and checking the design to ensure that the key functional requirements are still preserved and compile according to the pattern. We plan to use this approach to automatically plan the migration as the evaluation process. Thank you so much.